Exercise 13.18 is a difficult problem, and if you're pressed for time and you have to prioritize the things to study in this homework set, you'll want to complete this. You'll want to complete the work for exercise 13.18 in the homework set, but I would not prioritize going through this problem over and over in the way you might prioritize other exercises. If you look at this first exercise, and what you'll notice is that there are similarities between each of the two compounds. So in both of them you sort of have this purple part that's the same. When you look at the other part, what you'll notice is that you have a bromine on the left. It's not there on the right, and what you have is a new carbon-to-carbon bond. Now all of those two features, the fact that you start with a bromine and you have a new carbon-to-carbon bond, those are hints, those are signs that you would have used a Grignard reagent here. You would have done a Grignard reaction. So when you just sort of look at the structures of this and analyze it, you might think, okay, this is just a typical Grignard reaction. All I have to do is a similar thing as I've been doing in the previous exercise on making alcohols with Grignard reactions. But this is a little bit more difficult, and it introduces a new concept that ends up being a really important concept in professional laboratories. It's the concept of protecting groups. Now before we discuss how this fits in with Grignard reagents and alcohols, I just want to make a note of one thing. That's that Grignard reagents react with OHs. That's whether the OH is in an alcohol or if it's in water. So if you put a Grignard reagent in water, it'll react with the OHs in water, and the Grignard reagent will be destroyed. And the reason it does that is because, remember, this bond here is almost ionic. It's really, really polar covalent. So you can sort of think of the carbon as having a lone pair and a full negative charge, and the magnesium as having a full positive charge. And if you look at the other molecule, the oxygen is really electronegative, pulls electrons to itself, becomes slightly negative, and the hydrogen that it's bonded to becomes slightly positive, and this carbon actually becomes slightly positive too. But the hydrogen is a little bit more vulnerable because it's small, it's exposed on the outside of the molecule. The carbon is protected on at least a couple sides, one by the oxygen and then by this other carbon there. And so it's a little harder to reach. So if you mix the Grignard reagent with something that has this OH here, the negative carbon will always do a proton transfer, attack the H on that, and just give you an alkoxide. So you'd be left with just a hydrogen on that carbon, so you just have propane gas, and then on this other molecule you would just lose the hydrogen. So you do a proton transfer, and it takes time and money to make Grignard reagents, and there are much cheaper and faster ways to make these alkoxides, so this is kind of a waste. Most of the time, reacting a Grignard with an OH is a waste. Now I mentioned, notice this the carbon chain doesn't have anything to do with this. The crucial thing here is the OH, and so this same reaction could happen with water. And so when you're making Grignard reagents, you can't use water as a solvent. You even have to be careful about how much humidity is in the air, because your Grignard reagent will get destroyed by the humidity in the air. Okay, so if you had, let's say you had a molecule like this, an alcohol like this, and you wanted to make it, just like in the previous exercises, you could say, oh, I can make an alcohol with a Grignard reagent. You look at the carbon that has the OH on it, take the rest of the carbon chain there, that's going to be your Grignard reagent. You'll just need the magnesium bromide on it, where the carbon was attached, and then the part that has the oxygen on it, you'd want to turn into a carbonyl. So you add another bond to that oxygen, and then I'm just going to put the hydrogens in there so it's a little bit clearer. And that's the foundation for your Grignard reagent. Now technically the Grignard will be the first step, and then you just want to stabilize the negative charge that will form on the oxygen, this oxygen here, with a proton transfer from water. And we walked through an example of how this worked a whole bunch of times in the video for the previous exercise. Okay, but what if, instead of just a regular carbon chain here, what if you have an OH on that carbon chain. So what if you have an OH on that carbon chain? Is the reaction, or is the process of making this molecule here the same as making the one above? In other words, can you say, okay, I want to make this alcohol. Let me just take this part right here, turn that into a Grignard, so MgBr. Then I'll take this part here and turn that into a carbonyl, like I did before. And notice these are really the same, or they're at least very, very similar, right? You have these 3 carbons here with the MgBr, 3 carbons with the MgBr. The only difference is that in this case, you have this OH here. So can you do this reaction? And the unfortunate truth is that you cannot. And the reason is, if you have more than one of these Grignard reagents, you wouldn't be able to form this Grignard reagent, because if you had more than one, the MgBr on one of them would react with the OH on the other through this reaction that we've seen above. So you would not be able to do this Grignard reaction because the alcohol that's already present would prevent you from forming that Grignard reagent. So are you stuck? Is there nothing you can do? There is something you can do. You can prevent the Grignard reagent from attacking that OH by doing something called protecting it. We can take this OH, which is reactive, turn it into something that's not reactive, do this reaction, and then turn it back. So for example, we could take this molecule we had in the beginning. Now, we would have the magnesium on there, but in order to do that, to get the magnesium on there, we would want to add the magnesium. So hold on a second. So we've got this molecule here. We can't have the magnesium there because if we did, one molecule would react with the OH on another. So we can't have that there just yet. Before we make that, we can protect that OH. In other words, and we'll talk about what specifically would go here, but you can put some sort of a group there that protects it. And now that that's protected, you can add the magnesium, make your Grignard reagent, do the Grignard reaction, and then whenever you have what's left, whatever you want here after that Grignard reaction, in the case above it was an alcohol, then you can deprotect it. You can take this off and get this OH back. So you're still doing the same reaction. You're still making the Grignard reagent and reacting it with an aldehyde or a ketone or a carboxylic acid or an ester. You're still doing that. But you have to protect this, you have to protect that OH first and then deprotect it later so you get it back. It's kind of like if you've ever painted a room, it's really a pain to paint the corners. You don't want to change the corners, you just want to change the middle of the wall. And so what you'll do is you'll put a sort of painter's tape on the corners so that when you paint them, you don't mess that up. So really what these protecting groups are is sort of like painter's tape. You can put painter's tape over them, then you can do surgery on your molecule, paint over all different parts of your molecule. It won't affect the thing you put painter's tape over, and then you take the painter's tape off and you get that group back. Okay, now for alcohols, here I just put an orange blob, but how do you protect an alcohol? Really what we want to do is make that group really unreactive. The problem is that this will react with our Grignard reagent. We want to turn it into something that is very unreactive. One molecule that is unreactive are ethers. Now we haven't discussed these. We'll have a chance to discuss these in more detail in the next chapter. But you have water. If you replace one of the hydrogens in water with a carbon, then you have an alcohol. So alcohols are derivatives of water. If you replace the other hydrogen in water with another carbon, then you have what's called an ether. And as we'll see in the next chapter, ethers are extremely unreactive. There are very few things you can do with ethers. That makes them really good solvents because they won't interfere with whatever reaction you're interested in. And it also makes them good protecting groups. Now, that's good for protecting the OH. We can turn it into an ether, but it's not good for deprotecting it because it's really hard to break ethers. It's a violent reaction. So instead of using ethers with a carbon, we're going to make ethers that are a little easier to break. We're going to make ethers with the element that's immediately below carbon on the periodic table. That's silicon. So it'll have similar chemical properties, but it will be easier to break these silicon ethers. And so we can deprotect them more easily. We can put them on just as easily, but we can take them off more easily than we would be able to do with the carbon ether. So instead of having a carbon there, we'll have a silicon on one side, and that's silicon ether. Easier to deprotect. Okay, the specific silicon ether that we're going to use is called trimethyl silyl. It's called a trimethyl silyl ether. And the way we're going to make it is by using a reagent called trimethyl silyl chloride. So the silyl is just referring to the fact that you have a silicon. So silicon. Trimethyl, that means you're going to have 3 methyl groups coming off of this. So the methyl group is just a CH3. I guess I'll put an ME here. Remember that ME is standing for a CH3. It's a methyl group. That's not standing for an element. So trimethyl, you have 3 methyl groups coming off the silicon, and then the 4th bond here, silicon is in the same group 4A as carbon, so it forms 4 bonds just like carbon does. The 4th group is going to be a chlorine. So that's trimethyl silyl chloride. Now what you can do is you can take your alcohol that you're interested in, and that slightly negative oxygen can act as a nucleophile. Chlorine is also very electronegative, so it's pulling electron density away from the silicon, which is slightly positive. And you can actually do an SN2 reaction here. So this oxygen will attack the silicon and kick the chlorine off. Now, if you've really mastered substitution reactions, this should look a little strange because this is very crowded, right? The silicon is bonded to 1, 2, 3 other carbons. It's tertiary. You don't usually expect an SN2 reaction to happen on a tertiary atom. The reason why it can happen here is because as you go down and to the left on the periodic table, atoms become larger. And because of that, bonds become longer. And that keeps these groups further away from the atom, which means that the silicon is less crowded than a tertiary carbon would be. Notice silicon is below carbon on the periodic table. That means it's bigger than carbon. That means these bonds are longer. There's more distance between the nuclei of the carbon in this methyl group and the silicon. So the bonds are longer, so this is not as crowded, so you can do an SN2 reaction here. And what you get after that is this molecule here. So those electrons are going to go to form a new bond to this silicon. And actually, here, let me just draw this over. So you'll have that silicon with its 1, 2, 3 methyl groups. And then floating around in the beaker, you'll have that chlorine that was on the silicon. It'll be a chloride. Now notice this oxygen here has 3 bonds. You might remember from Organic Chemistry 1, when oxygen has 3 bonds, it has a full positive charge. And you can use the formula for the formal charge to calculate that, to confirm that. Now that's unstable, and so to stabilize this, we just need to get rid of this hydrogen here. And to do that, you use a molecule called triethylamine. That's a nitrogen with 1, 2, 3 ethyl groups here. Nitrogen is in group 5A, so it can form 3 bonds and it has 1 lone pair. And this can act as a base. So this nitrogen is slightly negative, and because it's a very electronegative element, each of these carbons is ever so slightly positive. And this nitrogen, with its slightly negatively charged lone pair there, exposed to the world, bumps into molecules and can rip hydrogens off of them. And remember, this oxygen pulls electron density towards itself normally. With a full positive charge on it, it pulls electrons to itself even more. This hydrogen becomes really slightly positive. And so it can act as a base, steal the hydrogen. That will snap the electrons back onto the oxygen and stabilize that molecule. Okay, now this is a mechanism that you will never be expected to draw in my class, but I wanted to show you this to you because when we start to do the synthesis exercises in this when we start to do the synthesis in 13.8, we're going to be using what will look like just a jumble of random letters. And I want you to see what those letters stand for and what reasoning stands behind them. So if you do this reaction, what you end up with are 2 things. Both of these things are going to be important. The first thing is you have now protected your alcohol with a trimethylsilyl ether. And this hydrogen goes to the nitrogen. The nitrogen now has 4 bonds, and so a full positive charge. Let me just get those partial charges away so they don't distract us. Okay, so this is our protecting group. This whole thing is our protecting group. That's a lot like this orange circle that I had up there. Now this was a lot to write out. This is a big molecule and it's clumsy, and so you won't want to write it every time you do a synthesis. So the abbreviation for this trimethylsilyl chloride is TMSCl. So T for tri, M for methyl, S for silyl, and Cl for chloride. So TMSCl is going to be a protecting group. And what you have to include with it is this triethylamine. Now the way this will look is an ethyl group is an ET, right? Just like a methyl group, CH3 is an ME. ET stands for an ethyl group. That's a CH2CH3. So we'll have 3 of those. 1, 2, 3. And then the nitrogen. So when we protect an alcohol, we're going to protect an alcohol with TMSCl and ET3N. This is trimethylsilyl chloride and triethylamine. Okay, so that'll protect our alcohol. Then we can do the Grignard reaction. We can make the Grignard reagent, do the Grignard reaction, and then we want to deprotect this. We want to take that trimethylsilyl group off. Now, the most common way to do that is to use this as a sort of leaving group, and and to give something else for this silicon to attach to. Now, I drew just a regular arrow here, but that's technically an equilibrium arrow. So you could the oxygen here still has a slightly negative charge, right? And this as a full that hydrogen has a really big, slightly positive charge. Nitrogen is stealing electron density away from it, just because it's electronegative, but it also has a full positive charge to pull the electrons to it even more. So this hydrogen is really losing its electron density and is very slightly positive, and the oxygen can steal it back. The electrons would go back onto the nitrogen, and that would give you back this scenario here. So these 2 exist at the same time. This is constantly turning into this, and this is constantly turning back into that. These 2 molecules are sort of like 2 kids fighting over this hydrogen toy, and now one has it and now the other has it. At any given time in a population of these, when you have hundreds of millions of these molecules, some of the ammonias will have the hydrogen and some of the oxygens will have the hydrogen. So we still have sort of this in solution in this equilibrium. So we can take that and use that to our advantage. We can take this and sort of think of this whole group as a leaving group. And then we would just have to deprotect this thing. We'd have to take that protecting group off. So we want to remove this orange protecting group. And so what we need to do is to attack it with a nucleophile that's going to stick to the silicon even more than an oxygen would. And experimentally, the nucleophile that works the best for that is a fluoride ion. That's fluorine with a full negative charge. And hopefully that does make sense. Fluorine is the only element on the periodic table that's more electronegative than oxygen. So it would make sense that it would have this sort of more intense negative charge that it would use to stick to that silicon even better than the oxygen does. Fluorine needs a molecule to be stabilized by, and the molecule that the fluorine is usually stabilized by is something called tetrabutyl ammonium fluoride. That's in a nitrogen, that's the ammonium part, with 4 tetrabutyl groups. So 1, 2, 3, 4. Remember, a butyl group has 4 carbons, that's one butyl group. 1, 2, 3, 4. It's a second butyl group. 1, 2, 3, 4. It's a third butyl group. 1, 2, 3, 4. That's a fourth butyl group. This is tetrabutyl. Ammonium, that's the nitrogen, and fluoride. When nitrogen has 4 bonds, it has a full positive charge. So this full positive charge is sort of balancing and stabilizing the charge on that fluorine there. So this is a source of fluoride ions, tetrabutyl ammonium fluoride. And when you add that to our solution, this can swoop in, attack the silicon, the electrons go back onto this oxygen, which had a positive charge that's going to be stabilized now, and you can get your alcohol back. So you would get just your original thing. So we deprotected this. We got the alcohol back. We removed the protecting group. So to deprotect something, we're going to add this source of fluoride ions, tetrabutyl ammonium fluoride, and that's a mouthful, so there's an abbreviation for that too. T for tetra, B for butyl, A for ammonium, and F for fluoride, so TBAF. TBAF will deprotect the group. It'll take the TMS off of the molecule. And so what we're going to do when we deprotect this is we're going to use TBAF. So really, if you want to do a Grignard reagent, but your Grignard reagent already has an OH on it, then all you have to do is first add TMSCl and ET3N, so trimethylsilyl chloride and triethylamine. That protects the OH. Then you can do your normal reaction. Make the Grignard reagent, do the Grignard reaction, and then to take this trimethylsilyl group off, you deprotect with TBAF, tetrabutyl ammonium fluoride. So the big idea, those are the specifics for protecting alcohols. The big idea here is that, and this will recur with other functional groups besides alcohols, the big idea is if you want to just focus on one part of a molecule, if you want to sort of do surgery on just one part of the molecule, and you don't want other parts of the molecule to interfere, you can use protecting groups that make those other parts of the molecule very unreactive. You do your surgery, and then you deprotect. You take the protecting group off, and you have your original molecule again. It's an important concept in organic synthesis, in making molecules, because real molecules often have many reactive parts to them, but often you just wanted to change one of them. So you'll protect the other ones, do your changing, and then get them back, deprotect them. So I wanted to go over that concept in this video. In the next video, we'll go through the actual exercise, 13.18, and we'll see how, and in that video, I won't be explaining what these terms mean. Right? We've already talked about that in this video. Instead, we're just going to be using them, and you'll see how we can frame our normal Grignard reaction with just this in the beginning and this at the end. Protection at the beginning and deprotection at the end.